Let's look closely today at what happens when two sound waves interfere with each other. Remember when we looked at standing waves in a string? There was this point in the middle where we always got destructive interference. We always had a crest meeting a trough to totally cancel each other out. So there was never any vibration right there at that middle point. So then let's look at standing waves in a pipe that's closed at one end again. These nodes here at the end and here in the middle, those are also locations where a crest, or in this case a rarefaction, is meeting its opposite, and they're totally canceling each other out. So at these nodes, there's no vibration at all. We actually have sound interfering with sound to produce silence. That's also the idea, behind noise-canceling headphones, where you actually have sound waves coming in, and the electronics of the headphones send in the anti-sound, the exact opposite, so the two sound waves interfere to block out all of the background noise. You can actually hear two sound waves interfering destructively in the phenomenon of beats. Here's the sample. You have a blue wave and a red wave interfering with each other. And you can see that here, for instance, the two waves are totally out of sync with each other, out of phase, and so they interfere destructively. Whereas there are other points, like here, where they're totally in phase with each other, so they're going to interfere constructively. Destructively here, constructively here. And so you'll hear a sound that is loud, soft, loud, soft, loud, soft. These are two frequencies that are very similar. Let me see if I can play something for you like this. Here's a 600 hertz tone and a 602 hertz tone. You can hear that vibration that they have, that loud, soft, loud, soft. It gets more frequent when the second frequency is farther off from the first. But as the sound waves get closer to each other, you can make the beats totally go away. Another interesting example of sound waves interfering with other sound waves is in the case of a single instrument playing a tone. So that's a guitar string playing a note. And when you hear it, you think, oh, there's a single tone there. But in addition to vibrating at its fundamental frequency, the string also vibrates at its higher harmonics at the same time. And that combination of harmonics that you hear allows you to identify that as a guitar string when you hear it. This is what we call timbre, which is another name for sound quality. So look at a tuning forks wave. It's pretty much a pure sound wave. And so you just hear a single tone. A flute playing the same tone has a slightly more interesting waveform. It has some higher harmonics mixed in to the fundamental, and so it's a slightly more complex wave. So you hear a different tone, and you would say, oh, that's a flute, not a tuning fork. A voice has a more complex sound, and a violin has a different combination of harmonics mixed in with that fundamental. So when you hear it, you think, oh, that's a violin playing the same note as the tuning fork. Here's a different way of looking at it. These are Fourier transformations of the same, or of a guitar and a piano playing the same note. What you see is that guitar has a lot of the first harmonic, the fundamental, and a lot of the second harmonic mixed in, and then not so much until the eighth harmonic. With the piano, playing the same note, you see a little less of the second harmonic and very little of the third, but more of the fourth. A completely different combination of harmonics, or amounts of the harmonics mixed into the fundamental. And so when you hear a piano play the same note as the guitar, you can clearly tell the two instruments apart from each other based on the combination of harmonics you hear. Interestingly enough, this is the idea behind how a synthesizer or very inexpensive keyboard works. When the manufacturers put this together, they basically start with a single sine wave, and they continue to add various amounts of different sine waves to it. And so you can create the illusion of different instruments playing that same tone because each of them has a different mix of harmonics mixed in with the fundamental. In fact, anytime you hear any sound at all, you're hearing a single interference pattern formed by all the sounds being produced at that instant. For instance, that complex wave you see on the screen sounds something like this. What's fascinating is that your brain hears that one interference pattern and still can pick out all of the different instruments that were, or at least many of them, that were being played when that song was being recorded. So let's look at the math behind beats. When you hear those two tones that are interfering with each other and you get the wah, 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 the number of vibrations per second that you'll hear will be the difference between the two frequencies. So if you had a 440 hertz tone and a 444 hertz tone interfering with each other, you'd hear 4 beats per second. The tone that you would hear, the tone that you would identify as you heard those two tones interfering would be the average of the two. So 444 and 440, you'd hear 442 hertz as the tone. Here's a different example. You try this one. A 440 hertz tone interferes now with a 438. The number of beats per second? Yes, of course, that would be 2 beats per second. And the tone that you would hear, yep, that would be the average of the two tones, or 439 hertz. Let's get more technical with the analysis. Here you see an oscilloscope's read output from two tones that were being produced at the same time. First, what you need to know is that this timestamp up here tells you that the highlighted portion of the window took 0.138 seconds. Next, we look at the fact that we have 1, 2, 3, 4 beats during that time period. So the beat frequency would be 4 beats divided by 0.138 seconds, or 29 beats per second. So that tells us the two frequencies must have been 29 hertz apart. Next, we have to figure out what those two tones were. In order to do that, it takes a lot more work. Now we have to count all the individual crests during that 0.138 second time interval. Excuse me, I approximated that to be about 68 waves during the 0.138 seconds. So the tone that you would identify when you heard these two tones being played at the same time would have been 493 hertz. So that means one of the tones must have been half of 29 higher than that, and the other must have been half of 29 lower than that in order for the two tones to average 493 hertz. So that would give us a tone of 507.5 hertz, and the other lower tone would have been 478.5 hertz. This is a kind of analysis you'll get to do for homework for tonight.